So you just learned the fundamental theorem of calculus, or at least the first part of this theorem. So how do we use this? Let's pretend that we're looking at the function x squared, and we want to find the area under the curve from x equals 1 to x equals 2. We would typically write it this way using integral notation. What we've now learned is we need to figure out the antiderivative of this function, and once we find that, we plug in a 2, and then we also plug in a 1, and we subtract the one that has 2 from the one that has the 1. So the antiderivative, we'd raise the power by 1, so we get a 3. We multiply by the reciprocal if we're undoing the power rule. And then we put the limits right here. That's just a new way, I suppose, of where we put limits when we've already done this antiderivative business. And then from there we would plug in a 2 into that antiderivative, plug in a 1, we're subtracting the 1 from the other. And this is something that hopefully we could do without a calculator. 2 to the third is 8, so we have 8 thirds. And this would be 1 to the third, which is really 1, so don't need to worry about that power. And as we subtract, we get 7 thirds. So hopefully that is clear enough, just using antiderivatives now to help us find the area under a curve. Now, if our textbook ever uses the term total area, what they don't want us to do is, let me go through here a little bit, they don't want us to count this as negative. They want us to figure out a way to count this as positive. So if we were looking at cosine of x, we hopefully have we could think through at least what cosine of x looked like from 0 to 3 pi over 2. We know that we have a first part is positive, a larger chunk that would normally be negative, but they want us to count it as positive when they use the term total area. Typically AP questions will not use this. They would make it very clear in other ways that they want you to count everything as positive. But if we know what this graph looks like, we need to find one integral that's going to go from 0 to pi over 2, and then another one that's going to go from pi over 2 to 3 pi over 2, and because this would be negative, if we think of subtracting it, it would count as positive. You could certainly show this work in other ways. Just do this on your own, and just whatever answer you got there counted as positive. So anyways, the antiderivative of cosine is sine. So we want to do this with sine. We want to plug in a pi over 2 and then plug in a 0 and subtract 1 from the other. And then the same thing over here, plug a 3 pi over 2 in and a pi over 2 in and subtract the second from the first. So we do all this work, we get this. Hopefully we can think through unit circle stuff. Sine of pi over 2 should be 1 minus sine of 0, which is 0, and then minus or whatever you get from here. Just make sure you count as positive in the end. Sine of 3 pi over 2 would be a negative 1 right here. Sine of pi over 2 should be a positive 1, I guess, but we're subtracting it. So as we go through all that, we get this. Just be very careful with signs, but in the end we should get an answer of 3. So hopefully that is clear enough. Jot down some questions if you have them. But these would be two basic examples, I would say. Our next examples will go through some u substitution review. Example 3, what is the integral of tangent of x times secant squared x from 0 to pi over 4? So I have no idea what this graph looks like, but we need to recognize the power of antiderivatives to solve this, and we also need to look back and kind of remember some of our antiderivative rules. So in this case, because I see several functions here, and I need to think about how the derivative of one might get me the other one, I'm actually going to make u equal tangent of x, because I recognize that du, the derivative of this, would be secant squared. And so typically, I think when we learn this, I've more than likely told you to solve for dx and just replace it here, but hopefully you can see that this whole thing right here, secant squared x dx, would just be du. So all this is going to be replaced with a du, and this will be replaced with a u. The other thing we need to do is typically find new limits for this integral. because these limits right here are for x values, and if I'm going to be using u now, I need to get limits that are also u values. So this is new. This part is very important. I'm going to take my limits here, plug them in for the x right here, tangent of x, and get u values that would kind of get us better limits that match up with the variable that we're using. So u of 0 would mean find tangent of 0, which is 0. And u of pi over 4 is tangent of pi over 4, which is 1. So in the end, here's what I want to see, that my new function is u because everything else has been substituted through u substitution, but I also have to put new limits. Pi over 4, when I plug that into this equation right here, I got 1. And 0, when I plug that in here, I still have 0. And now I go through this whole antiderivative business. So for the antiderivative, raise the power by 1, I have u squared. That means I multiply by the reciprocal as well. So I have a 1/2 in front. Put the limits right there. And if I plug a 1 in and I square it, I still have 1. And then multiply by a half, I get 1/2. And hopefully we can understand if I plug a 0 into this particular equation, I get nothing. So in the end, 1/2 is my answer. If you prefer, there is another way to do this. We could have gone through a little bit of work of doing the u substitution, plugged in tangent of x, and still used our original limit. So I want to run through that a second, but I think most of the time you are going to use the method that I just showed you. So if we did the original limits, we'd go through and do our substitution. However, this would be wrong, okay, because I have a u. Oops, hit too many buttons there. I have a u right here, but these are values for x. So typically in our work, we would just show the antiderivative. We would not put limits in here right now because we haven't figured out these new ones. I'd go through and do the antiderivative business. And then once I get to this point, I know that u equals tangent of x. So I'd go and replace u with tangent of x, and then I can go ahead and put the original limits in there. And then at that point, I plug in pi over 4, I plug in a 0, I go through and I do the work, and I would still get 1/2. You're basically doing the same exact work, just in a different order. I tend to feel like doing it this way, though, you end up doing more work. I would encourage you to do example 3 using the first method rather than this method that's on the screen right now. And our last, our last example for today. Maybe a more typical u substitution example. Hopefully you can remember that we look for the function that's on the inside, so x cubed plus 1 would be on the inside, and when we make that u, that derivative equals 3x squared dx, which is a good thing because 3x squared dx is going to replace these two parts with the du. So again, I might have shown you different work when we first learned this, just we're kind of looking at this in a very slightly different way here. But we have a 3x squared and a dx, so I would take those two parts and replace them with the du. And I would end up with, oops, I'm going to find my new limits here, sorry about that. I plug a -1 into this function here, so if I plug a -1 in, I get -1 plus 1 is 0. Do the same thing with 1. When I plug a 1 in and cube it, I get 1 plus 1 is 2. And so now I can write this as u to the 1/2, because all of this is u. We're taking the square root, so really a 1/2 power there. These two pieces here were replaced with the du. I now have new limits. So I need to take the antiderivative of u to the 1/2. So I raise the power by 1, I get 3/2. And that means I also multiply by that reciprocal, so multiply by 2/3. Use the new limits there of 2 and 0. And I plug them in. So again, if I plug a 0 into this, I'm going to get 0. I don't need to worry about the second part of this right now. But I would need to worry about, obviously, the limit of 2. Now, when I do this, a couple ways to think through this. This PowerPoint's kind of going right to 2 root 2, and you certainly could probably use a calculator to get an equivalent answer here. The way I would think through this is you take 2, you're going to cube it to get 8, and then this 2 right here means you take the square root. So what's the square root of 8? it's equivalent to 2 root 2. If we need to go over that in class, just ask. And then the 2/3 is still out there. And if we simplify that, we get 4 root 2 over 3. So that should be our final answer for this last example. So jot down any questions you might have, but hopefully this showed you a few ways that we could use this first part of the fundamental theorem of calculus.